Hello everyone and welcome to Texas Tech University's Project Lab 1 tutorial videos. I am one of the tutors for this course. My name is Daniel, and in this video I'm going to be showing you how to create a PWM signal from a module on the BASYS2 board. So to get started, we're going to talk about what a PWM signal is. You should have talked about it in Digital System. Not you can go to Google and search PWM. There's various different resources that explain PWM and several tutorials on how to create PWM. But basically, PWM is a technique. It's called pulse width modulation, and it's a technique to create these different width pulses to get different outcomes on a digital system. So as we know, our BASYS2 board outputs a logical 0 or a logical 1 through its outports, so PMOD ports or any other general I/O port. So that 0 on the BASYS2 board, this logical 0 is 0 volts, and for the BASYS2 board, the logical 1 would be a 3.3 volts. So I know this image shows a 5 volt for the logical 1, but this is just an image for the Arduino here. So in the BASYS2 board, we do have a logical 1 represented as 3.3 volts. Do not want to take any 5 volts, anything higher than 3.3 volts. You will damage the BASYS2 board and the input pin. Alright, so pulse width modulation again is just a technique to create these pulses, and these pulses get created by a sequential 1, so a bunch of 1s and a bunch of 0s. They get repeated in a set period, so different components run at different periods. Period can also be thought of as the refresh rate on whichever component you're working with. So if you're working with a servo that has a refresh rate of like 60 hertz, your period would want to be of 60 hertz, so that way you are giving it the signal it needs at the time it's looking for it. Alright, so again, in this set period, here we can see that in this set period it is constantly off, so it is 0% on, so the duty cycle, we would call this having a 0% duty cycle. Here we see that the signal in this one period is on for 25% of the time, so therefore we would say it has a 25% duty cycle. This one 50 and 75, and then this final one you would see that it's 100% of the time on, so therefore it has 100% duty cycle. So what this does to a component that you're working with, so say if you're working with a motor, this PWM, this pulse width modulation technique, allows us to control the speed of the motor. So in this 0% duty cycle, we have 0 power going to the motor, so therefore it wouldn't be moving. In this 25% duty cycle, it would be moving about 25% of the speed, because we have 25% of the power going to the given motor. And in this one, 50% of the speed and 75% of speed and full 100% speed on the motor. So when you start working on your module to control the H bridge to drive your tank or your rover, you will see that the H bridge has 2 pins, an enable A and enable B, that can take a PWM signal and allows you to control the speed for that motor. So the H bridge is broken up to the A side and the B side, and enable A allows you to control the speed on A side, and enable B allows you to control the speed on the B side using this PWM technique. Alright, so another application that PWM is used for is to turn on or brighten up an LED or a light. So here you see that with a very thin, narrow pulse, the light is almost off. Here with a half pulse on, you see that it's a little bit brighter. And here with an almost full pulse, you see that it's the brightest. The LGB or the RGB LEDs, the red, green, blue LEDs, also use PWM to change the different colors. So it has a red and a green and a blue leg that if you change the PWM on each one of the legs, the LED turns on a different color. Another application for PWM is for the servo. Creating pulse widths of certain size will move the servo to a given position. So this is just an example of, I'm sure it's not a real servo, the specs, the period, and the pulse width for each servo should be given in a data sheet. So if you grab a servo from the stock room, go to the data sheet and it'll tell you what the period should be and what the pulse should be for that given position, and then it should tell you for center position and for furthest right position. So to operate a servo with PWM, you can get with me later and I can show you that. But in this module we are just going to create the basic PWM and simulate it through the Verilog ISC webpack. So opening up my ISC webpack, okay, so now that it's open, I will create a new project. So let me close my tip of the day, file, new project. I'm going to call this PWM underscore tutorial 1, and it's HTML type. Hit next. Here's all the settings you want. Hit next and finish, and this will open up a blank project that we can start creating a module. So I right clicked in the empty view here, select new source. We want to select Verilog module. I'm going to call this PWM underscore tutorial 1. Hit next. And for our inputs, we're going to have an input called clock, an input called speed, and an input called reset. Then we're also going to have an output called PWM. Alright, so that's all of our inputs and outputs. We can hit next and finish. This will create a template blank module for you. So as you see, it just has the header on it and the inputs and outputs that we specified. I created this module a few minutes ago, so I'm going to Control C, paste this in here, Control V, get rid of the old name, and now let's go ahead and talk about this code that I wrote. So it has the same inputs and outputs, but what we see is that I added a size to speed. So here input is, since I didn't specify the size, it defaults to 1 bit. This reset input is also 1 bit, and this output PWM is also 1 bit. So on this input called speed, I assigned it to be a 2-bit input, and for it to have a position 1 and a position 0. Here I'm designating position 1 to be on the left and position 0 to be on the right. That way designating the most significant and least significant bits. So this is the way to create an array and specify most significant and least significant bits. Clock, we'll connect that to our oscillator clock on the BASYS board. Reset, we can connect this to a button, and PWM will be our signal that we can use for our motor, servo, LED, or whatever we need. Okay, so here next. So first you should see that there's an error with my inputs and output designation here. In in standard Verilog, you do not have a comma on the last entry of your input and output. So I will delete that comma so we don't get an error later. And then we see our 3 registers. This register is going to be the counter. And the counter, we can think of it as our period. So here on this image, the period goes from green line to green line. And you see that the signal gets replicated every period. So like we said, each motor or servo operates at a certain refresh rate. So that would be the period that you want to refresh the signal for that given device. So the period is going to be just a counter that we increment to a set size, and then once we increment that counter past its maximum size, it will reset itself back to 0 and start counting back up. So in this case, our counter is 5 bits. So if we want to know how big of a number we can put in 5 bits, we can open up our calculator and do 2 to the 5th and see that a 5-bit number can only count from 0 to 31. So it only has 32 positions, and you have to include the 0 position. So from 0 to 31 is what we can count on our counter. So with that in mind, we can think of this counter going from 0 to 31, and then at 31 all 5 bits are 111 are 11111, and then after you increment a 1, it resets itself to 0 and continues incrementing back up to 32 or 31, and then resets itself back to 0, back up 31, resets itself to 0, and continues to create this set period. So this counter, we just talked about it, it sets the period. So like a binary number, once it fills itself back up to 1, so it fills itself up to its maximum number, you increment 1, and then it equals 0, 0, 0, 0. It actually increment equals 0, 1, 0, 0, 0, 0, but since it's only a 5-bit number, this last one doesn't matter. So it goes back to 0. And then it can start all over, counting back up to 1, 1, 1, 1, 1, 1, and incrementing a 1 to set it back to 0. If you wanted a different period, so I know this period is going to be real fast. It's going to refresh really, really fast because it's going to fill up to 32 really quick on a 50 megahertz clock. So if you wanted a different period, so to calculate whatever period you want, so say we want a 60 hertz period. We know that the clock on the 50 megahertz on the BASYS2 board is 50 megahertz. So there's 50 million, and we want a period of 60 hertz. So we know the clock on the BASYS board is 50 megahertz. So it counts up to 50 million in 1 second, and we want to create a period of 60 hertz. So we want to create 60 times in 1 second. So to do that, we get our 50 million clock and divide it by what we want it. So divided by 60 hertz. And that tells us how many ticks we need. So how many ticks from the 50 million megahertz clock or 50 megahertz clock we need to create the 60 hertz. So we need to count all the way up to this number to create the 60 hertz. So we fill that up, and that's 1. And you fill it up again, that's 2. Fill it up again until 60 times. And that's how we create a 60 hertz period. So in our case, we're only going up to, what is this, 32? So we have a really fast period. This is the reason I'm doing it really fast period is to show you in the simulation that it does create different speeds and different size widths. If I created a 60 hertz clock, the simulation would be so big it would not fit on the screen. You would not be able to see the change in the width on this screen. So that's the reason I use a small counter. Again, for most typical applications, you're going to use a really large counter of 13 bits or bigger to create the refresh rate that you need. Alright, this next register, width will be the register that controls the size of the width. So as we said, our first register, counter, stores the size of the period. Now we have to designate a new register to store the size of the width. So that's width. Width will be the size of the width we want based on the input speed. Alright, so I'll explain a little bit more here in the code on how counter and width create the PWM. So this last register, temp PWM, as we know, you cannot manipulate an output directly. So a common technique is to create these registers called temps, and we can manipulate temps in this always at block. And then once we are ready, we will assign that temporary register to its appropriate output PWM. So this is a common technique used in Verilog to assign an output based on the different settings or the different inputs that you need them to be. So that's what temp does. Here, this block 32 to 36. This initializes all of our registers. So here in this line, we increment counter to be counter plus 1. So without this initialization of 0, Verilog would not know what counter plus 1 would be, so we need this initial begin to give it an initial value. This initial begin only happens once, and it will not affect the rest of the code. So here's the next block we see is this always at pause edge block. This block, an always at block, evaluates this argument. So here we say that always at every time we see the positive edge of a clock. So as we know, the clock oscillates from 0 to 1, 0 to 1, 0 to 1, and it does that 50 million times in 1 second. So as we identify the positive edge of the clock, the rising edge of the clock, we will do everything inside this begin and end statement. So here in this begin and end statement, we have two if and else statements. This first one says that if reset is pressed, so if reset is true, it will reset counter to 0. Else, if reset is not pressed, it will increment the counter. So this first if statement is just incrementing the counter every time it identifies the rising edge of the clock. This next if and else statement, it sets the PWM, so it sets the pulse to when it needs to be a 1 and when it needs to be a 0. So as we identified, width is going to be the register that stores the set width we want. So if we scroll down here, we see that width gets assigned based on speed. So here we say that if counter is less than width, so looking back at the image, if the counter, so again the counter goes from left 0 all the way to 31 and then resets back to 0 all the way to 31. So if the counter is less than the desired width, where the output temp PWM is going to be a 1 and else temp PWM is going to be a 0. So that is how we are assigning the 1 and the 0 to create this pulse width. So again, this if statement says if counter is less than width, temp PWM is 1, creating the pulse, the one part of the true part of the pulse width here, and else, so pretty much if it's not, it'll create the 0 part, the trough here. So this if else statement creates the pulse width, and next we see that there's this always at star here. Always at star, what this says is every time anything changes. Star says anytime anything changes, and like we said, it's always at whatever this argument is. So anytime anything changes, we would do everything inside this begin and end statement. So inside the begin and end statement, all we have is a case statement. So here's a case, and the argument for the case is speed. So remember, speed is our input. Our input is 2 bits. So the 2 bits can go from 0 to 3. So that gives us 4 options, 0 to 3. And based on those options, we make width the value that it needs to be to create that duty cycle. So like we said, our counter goes from 0 to 31, so our period goes from 0 to 31, 0 to 31. And to create a 25% duty cycle, you would divide 31 or 32 divided by 4. It would give you 8. So then we would set the width at 8 to create that pulse of 25% on and 75% off. So as you see here, if speed is 0, then width is also 0, and that'll create the 0% duty cycle. And if speed is 1, the width will be 8, which will create the 25% duty cycle like we just said on the image. And if speed is 2, we'll set it to the width to 16, which is right in the middle of 32. So that would create 50% duty cycle, and then so forth, so on. So as you see, we only have 4 different positions here because our speed is only 2 bits. So if you wanted more positions in your speed or your servo mode or positions or intensity of the LED, then you would increment the size of speed. You would make it, instead of 2 bits, 3 bits. So 2 bits gives us 4 positions, 3 bits give us 9 positions, 4, 16, and so forth, so on. So depending on the size of speed, you can have however many options you need. So here, just for speed and simplicity, I only did 4 options. Again, just to explain this case statement real quick, this is the argument, and what's left on the colon here is the argument. So we know it's 2 bits, and here if it's decimal 0, then we want the width to be a 5-bit decimal 0. So here it says if speed is a 2-bit decimal 1, then we want width to be a 5-bit decimal 8. So this is the value in decimal that we want to store in width, and this is the bits that width is. So it will automatically convert the decimal value 8 into its appropriate bits and store it in width. And same thing with this, it'll automatically convert its 2-bit binary to decimal whatever one you are referring to. So that explains the case statement. Again, default would be the default. If it's anything else, which I guess it could not really be anything else, but I always add default just in case. So that explains this always at block. And then finally here we assign our temp PWM, which gets manipulated up here, to our output PWM. So that pretty much explains all of the code. We can go ahead and save this and synthesize it. So make sure it's highlighted and double click synthesis. Alright, so great. So blocking and non-blocking. I wanted to make sure I talked about that, and good thing this reminded me. So blocking and non-blocking, you see this less than or equal to sign. And you see how sometimes we assign a value with this less than or equals to sign, and sometimes we assign a value with just the equals to sign. So these are blocking and non-blocking assignments. So this one would be a blocking. In blocking, it creates a sequential mode where the next line will not be allowed to happen until this first line completes. So that's what the term blocking is called. So it blocks the next line from happening, creating this sequential order. And this non-blocking, if we had so if all three of these were non-blocking, so if all three of these were like this, then they would all happen at the same time and not at a sequential order. So the error it's given us, it's because I saw it down in the case statement. I forgot to add a non-blocking to this case statement. So a typical rule of thumb that I was taught when I first started writing Verilog was that anytime you use an always at statement, you want to use a non-blocking assignment so that it all happens at the same time and you don't delay your clock. So here we're having all this happen at the same time of this positive edge of clock. If we had blocking, then it would delay and then it would not happen at the same time of this positive edge clock, and therefore kind of defeating the purpose of it. So a rule of thumb is to always use non-blocking inside your always at statements blocks, and use blocking outside your always at assignments or blocks. So as you see, the only time I use blocking statements is for my assigns, and I use non-blocking for everything else, except for my initialization. I could use non-blocking for those also. That would actually probably be better because it would happen all at the same time, and therefore making my code more efficient. So now we can go ahead and save it again. So the error right before I saved it, the error said you cannot mix blocking and non-blocking. So you can do either all blocking or all non-blocking if you want, but that does, like I said, defeat the purpose of your positive edge statements, and it is more beneficial to use non-blocking inside your always at statements. So we saved it, there was no errors. We can synthesize, double click on that. There we go. Synthesis is complete. We can implement design. So as always, once you finish writing a module, the next thing you want to do is simulate it. And then after you run your simulation, then you want to generate the bit stream and program it onto your device. So just for time, I will not be programming it onto the device, but I will simulate this module to show you that it does work. So going from implementation to simulation, we can start writing the test bench for this. To write the test bench, you want to right click in here under simulation and hit new source. And we want to write a Verilog test fixture. Here I'm going to call it PWM underscore tutorial 1 underscore test bench. And this is just a standard naming convention that tells me this is a test bench for this module. And I hit next. Here it wants me to associate the module. The module is PWM tutorial 1. Hit next and finish. And then it'll open up the module, the test bench. So as you see, it looks similar to our module. The name is different, and instead of our inputs and outputs, we have a bunch of registers and wires. So if you've seen any of my previous videos, it'll tell you about instantiation and how this works. So if you want to know how that works, look at one of the other videos. For now, we're going to go ahead and start the stimulus. So to add stimulus, you just want to change your inputs. We know that clock is going to be an oscillator, so I'll show you how to generate the clock oscillation here in a minute. But our inputs that we would want to manipulate are speed and reset. So I'm going to Control C these, and I'm going to tab here, Control V here. And now we can start changing our inputs. So speed, I'm going to make it be a 1. And now I'm going to delay some time. So let's say 600 ticks. Again, if you want to see how these delays work, go back to one of our previous tutorials and I will explain all those. But what I will mention right now is that you do not want to use these delays in a Verilog module, because it will not work the way you would expect it to. These delays are only for test benches. So like a good test bench, you want to check all of your available options. So at first, speed is initialized at 0, so the PWM should be at 0 duty cycle. Speed goes to 1, so that would be 25% duty cycle. Speed goes to 2, that would be 50% duty cycle. Speed goes to 3, 75% duty cycle. And then I will briefly do a reset to test the reset. And then reset them back to 0. Alright, so that's pretty much most of the test bench. The only last thing we want to do is add the clock to make it oscillate. So to simulate the clock, all you have to do is an initial begin. I guess I misspelled initial. Make sure you spell it correctly. If you don't see it turn blue, you misspelled it. So initial begin, and we'll delay, let's just do 1, and then clock equals not clock. And end. So this will just oscillate clock. We know it started at 0, so it'll oscillate it to 1, and then it'll change it to 0 to 1 to 0 to 1 every tick of the computer, so as to simulate the clock. So That is how you make the clock oscillate. This is how we change all of our inputs. Our input options are only from 0 to 3, so we did all of our inputs 0, 1, 2, 3, and then we hit reset to see what it's going to do. So we can go ahead and save our test bench, and now we can highlight it here under hierarchy, come over to our simulator, hit that drop box, and double click on simulate behavioral model. And here it'll pop open the simulation that shows you all of your inputs and outputs. Here you can click on this zoom to full view to see that changes in the outputs. What we see is that the clock is not oscillating, therefore nothing else is happening. Oh, okay, so you need an always begin. So to get the clock, you want an always begin here, so that way it always oscillates it, and not an initial begin, which just does it once. Alright, so resave this test bench, double click on simulate behavioral model, and now hitting full view. Now we see that the PWM output is doing what it's supposed to. So moving here, we can go step by step to see that speed is at position 0, so therefore PWM is at 0. We see that PWM, or the speed, gets changed to a 1, and we see that that creates about a 25% duty cycle. And then when it goes to a 2, the PWM is at about a 50% duty cycle. And let's play some more. So we're at a 2 here. 2, we see 50% duty cycle. 3, we see 75% duty cycle. And play a little bit more. We see the reset being pressed there. So here's the reset. And reset resets the speed. And it sets PWM to 0. And now you see that speed goes to a 2, which sets PWM back to a 50%. So this simulation is a great way to verify that your code works, and it's a great way to demonstrate to your professor that you have a successful module. This module can then be used to control multiple motors by instantiating this module inside of a top module, and you can instantiate it multiple times. So the next thing you would want to do for this is go ahead and close out your simulation. We've seen that the module itself actually works the way it is designed, so we can move back to implementation and double click on generate program file. So that generates a bit file that we can program onto our BASYS board and program our BASYS board. So in future videos I'll show you how to do other things, and thank you for watching. I hope you learned something.